to compute the value of a line integral, we have to take the intuition that we had from the first activity, which was that we're trying to take a dot product of the vector field with the direction that we're traveling along our path, and then somehow use calculus to add up all of the infinitesimal contributions of the dot product of the vector field with our velocity along the entire path that we're moving along. So what does that end up looking like? Well, we can define it with one of these Riemann sums, right, by cutting up our path into a discrete number of steps and taking our displacement vector for each one of those steps and taking the dot product with the vector field, and then letting the number of slices of my path tend toward infinity. And so the delta r is going to tend toward the zero vector. And in doing so, the Riemann sum turns into an integral. And what we get is called the line integral. And the way that it's expressed in notation is that we write it as the line integral, so an integral with a little c underneath it to represent the curve, the path that we're taking, whether it's a straight line path or a curved path or whatever it might be. And the integrand we write as the dot product of f, the vector field, with dr. And dr is this teeny tiny little infinitesimal vector that points in the direction of in the direction that our parameterized curve is moving at each point. So it's f dot dr. So that dot product, again, is reminding us that what we're adding up is the parallel component of the vector field that points in the direction that my curve is moving infinitesimally at each one of the points on my curve. And so it's defined in a Riemann sum this way, but we're never going to use the Riemann sum formulation in this course to do it. What we'd like is we'd like to figure out a way to actually compute this integral directly, which we're going to do in section 12.3. But before we do, we want to finish gaining some more intuition about what the value of this line integral ought to be in a variety of different cases. So in activity number 3, what I'd like for us to do is not do anything computational, but to take a look at these two vector fields. So we have a vector field on the left, it's going to be called vector field F. Vector field on the right here is G. And we have 4 different paths, the paths C1 and C2, oriented with respect to the vector field F, and the paths C3 and C4 oriented with respect to the vector field G. And so the question here is going to be, do we expect the line integral of these vector fields along these paths to be positive, to be negative, or to be 0? And we don't need to do any calculation. We just need to sort of go back to our airplane example one more time, right? Where, for example, on the second leg of the airplane journey, we predicted, oh, that path integral ought to be 0. That amount of work ought to be 0 because the vector field and the velocity are perpendicular at every point. Meanwhile, on the first leg of the journey, the purple one, that line integral ended up being positive because the vector field made an acute angle with the velocity at every point along the way. So that same kind of reasoning is the kind of reasoning that you want to do here. It's just that now the vector field is not constant anymore, so it varies from the vector field arrows vary from one point to another. And also, at least in one of these cases, my path is no longer a straight line. And so my velocity vector is also going to be changing in direction as we move along. And so the question is, what on average in total is the vector field more parallel to the direction that we're traveling, or is it more anti-parallel to the direction that we're traveling, or do those cancel one another out and we end up getting 0? So take a moment and make your predictions for these 4 line integrals, positive versus negative versus 0. And after you've done that, we're going to go back into the Vector Field Analyzer 2 tool and have it help us to gain some more intuition for how this is happening. But make your predictions first, and then we'll use that technology piece to verify those predictions. All right, so far so good on this one. So you decided that the first of these, the C1 integral, that should end up being 0 because for the first half of our journey we're flying anti-parallel to the vector field, and so we're going to be getting a negative contribution in the path integral. But then after we cross the origin, we're flying in a parallel direction that's exactly symmetric to the amount of time that we spent flying in the anti-parallel direction. So the second half of this journey just cancels out what happened on the first half. Right? All the time I spent flying anti-parallel to the wind, I spend the same amount of time flying exactly parallel to exactly the same kind of wind that I flew in the first part of my journey. And so we end up getting a cancellation to 0. The Vector Field Explorer tool gives us actually a really neat way to look at this. So to use the vector field analyzer to study path integrals, you have to find a third tab in here. And so there's these little buttons that for me look blank, but I think they're supposed to be little arrow buttons. If you click the right one, it opens up the third tab possibility called line integrals over here. And so if we go into the line integrals tab, choose to show circulation, and then pick open curve, it lets me draw whatever curve I want to on this vector field, and it will visualize for me what is the line integral along that curve. So if I want to do this diagonal line, of course doing it with a mouse is kind of hard to get precise, but if I draw this diagonal line, notice how for a portion of it it's shading the line in a negative fashion. So orange shading here means a negative value for the circulation, the path integral along that piece. But then as soon as I cross the origin, now my path integrals are becoming positive again. And so if I could have drawn this to be exactly symmetric, I couldn't quite get it to work out. But if I could have done it exactly symmetrically, then I have exactly as much positive as I have negative here. And so the total amount is going to cancel out to 0. You then decided that for C2, this path that's going from east to west down here in the 4th quadrant for this vector field, that the vector field arrows are making an obtuse angle with my velocity vector at each point along the way. And so that path integral, we think, is going to end up being negative. And so if we try that in the vector field analyzer from about here to there, then it looks like everywhere along that path, the contribution is going to be negative, which is what we expected to happen. So that looks good. So far, so good. For our other vector field, which points downward in the left half plane and upward in the right half plane, when we take this semicircular path, C3, starting from over here and ending over there, at no point are we moving in a direction that is in any way parallel to the vector field. We start out moving in an anti-parallel fashion against the vector field, and then briefly the vector field kind of dies off at the y-axis. But then when we reemerge on the other side, we're still moving in a direction that is against the arrows rather than with the arrows. And so you predicted that the path integral in that example would be negative. And if I change up my vector field so that it looks like the example that we're looking at here, and then we try this semicircular path, actually it's kind of nice. We can have it draw a circle here. Oops. Let me clear that out and just try. So here's a circle centered at the origin. And it looks like this circle is being parametrized in a counterclockwise fashion. So actually I probably just want to do this with an open curve. That as we anticipated, we get negative contributions at the beginning. They become small when we get near the y-axis, but then they remain negative when we emerge on the other side. And so my total circulation, my path integral, is going to equal 0 for that path. And then finally, for the path C4, it looks like it is behind my head here. Sorry, let me move out of the way. It looks once again like the direction that we're moving is perpendicular to the vector field at every point. And so the path integral's value is just going to be integrating a bunch of zeros, because all those dot products are going to end up being 0 because our vector field is perpendicular to our velocity. And just to verify that, we can sketch in. We don't get any, except for my little shaky hand happening in here. I've had a little too much coffee today. We don't get any green positive, we don't get any yellow negative. It just gives us 0 because we're perpendicular to the vector field at every point that we're going along there. So yeah, Vector Field Analyzer 2 is a great tool to help to visualize what's happening just by drawing a freehand curve, if you like to. We're also, in the next example, going to have the occasion to try a rectangular path. Right? So if we travel this rectangular path in a counterclockwise orientation, then what is the total circulation going to look like? In this example, it's positive, because on this vertical side, we're getting a positive contribution because we're parallel to the field. On the horizontal sides, we're perpendicular to the field, so we're getting nothing. And as we go around this box counterclockwise, we get, again, positive as we go down this right side, because, again, we're being parallel to the vector field in that direction.